Good morning, students. And today's class, we are going to study about the Davison and GERMER experiment. This experiment is an experiment done in order to prove the wave nature of the electron. Okay, so electron is also a particle. Okay, so how the electron behaves as a particle as well as a wave are being explained in Davison and GERMER experiment. Okay. So this is an experimental setup of Davison and GERMER experiment, and we are going to see experimental setup like this. Okay. So this one. One minute. Enanga? Starting la light on irukudhe idu light on பண்ணல இது பாதி கட் பண்ணனும் போல இருக்கு 1 minute நான் பேசுறது திருப்பி இங்க வந்துகிட்டு இருக்குதே இங்க வரமா ஆல்ரெடி பேசுனது இப்போ வந்துகிட்டு இருக்கு வரதா செய்யணும்
just a minute no it won't come no
நான் பேசுனது வந்துகிட்டு இருக்கு
உனக்கு கேக்குதா என்ன
கேக்கல
அது
ஆனா இது வந்துகிட்டே இருக்குமா
அந்த zoomல it will okay now it's fine
I will start
you
fresh.
can continue
I will start
you continue okay no continue
கட் பண்ணி கிளிக் பண்ணிருங்க இப்போ இங்க வந்தது போனதெல்லாம் லைட் ஆன் பண்ணல
ஓகே பண்ண நீ கண்டினியூ பண்ணு லைட் பிரஸ் பண்ணிட்டல பிரஸ் பண்ணிட்டேன் அப்புறம் போயிட்டு தான் இருக்கும் முதல்ல பண்ணு இந்த லைட் பேட்டரி சார்ஜ் இல்ல
battery charge me okay I will just start fresh okay good morning students in today's class we are going to study about the Davison and the GERMER experiment. This experiment is basically done after this de Broglie concept of the matter wave, which we studied in the last class, as particles, okay, are traveling in the form of wave as well as having the particle embedded in it. Okay, the matter wave as proposed by de Broglie is that light particles are traveling, a photon is traveling in the wave form as well as having or embedded with the particles. So this he called it as matter waves. Okay, matter wave, which is a wave enclosing the particle in it. Okay, so after this explanation of the matter wave by the de Broglie, there is a need that the particle as well as the wave nature has to be proved scientifically. So later on, Davison and GERMER, okay, they tried to prove the particle as well as the wave nature of electron. Okay, electron, neutron, they are all particles. But if we can prove that these particles, when they are moving in an orbit or whenever they are moving in the form of a wave, okay, they are performing a wave nature, then it is easy to prove this matter wave concept. So Davison and GERMER, they had an experimental setup like this, and their aim was to prove, okay, their aim was to prove that electrons, okay, that electrons acts or move in the form of wave as well as in the form of a particle. Okay, now more in the quantum mechanics concept, we are going to move with the wave nature. So electron being a particle, when it is moving in the wave form, okay, then this concept of matter wave can be proved experimentally. So their electrical setup is like this. Their experiment, okay, they choose a filament, okay. These are electrical things in order to heat up the filament. There is a filament, okay, tungsten filament, okay. And there is an electrical setup in order to heat this filament to a high temperature. And once you know that when you heat a filament, due to thermionic emissions, there will be electrons that will be ejected outside from this filament surface, okay. And this electrons, when they are allowed to pass through, okay, they can be scattered, isn't it? There will be many number of electrons that will be ejected outside. So when they go out, they get scattered. So in order to concentrate on few electrons, or I can say 1 or 2 electrons, you can allow it to pass through a collimator setup, okay, arrangement, which can collimate the electrons to go through this. And there are some slit arrangements, okay, even when they come out, okay, their path is narrowed, okay, they are not allowed to scatter here and there, and they are allowed to gently pass through the slits arrangement, so that they will be taking a straight line path, and then they are allowed to hit the target material, okay. So the target material here chosen is a nickel crystal, okay. Are you able to see the nickel crystal, okay, at a glancing angle of theta? This is an incident angle. Theta is the incident glancing angle, I can say, incident glancing angle, okay. And after hitting the surface of the nickel, okay, electrons will, what happens exactly in this nickel crystal is that electrons will pass through this one, okay, and it will start penetrating into the layers. That's why I've drawn it as a lines, okay. The lines refer to the d planar spacing, okay. You have to imagine that there in an atom, there are rows of in a particular structure, crystal, you will have the rows of atoms like this, okay. So this row of atoms, I can draw it as a line, okay, and I can find the spacing between these two as a d spacing, d interplanar spacing. So when the electrons hit this target material, it can it will go inside and then get reflected outside, okay. Some of the electrons can go inside, okay. You know that the electrons, when it hits, when an X-ray is allowed to pass through a material, what happens is it goes inside and then comes out, okay. And some more goes inside and then comes out, okay. And the reflected beam of, there will be some, of course, scattered and they go outside also, but those which gets reflected at the proper, okay, on the atoms, okay, on the atoms in a particular atomic planes, okay, when they get reflected and when they are in phase with each other, okay, when they are in phase with each other and when their phase difference is equal to the path difference, okay, then there will be an interference that happens in this place, okay. Interference takes place here, and that will give rise to a bright image, or there may be destructive interference that can give rise to a destructive interference, okay. So this is what will be happening inside, and then you will find so in the interference you will get bright or dark images, okay. And here up to this is an electron moving as a particle, and after this scattering, okay, this is the scattering angle, this is an incident angle, okay. Phi is a scattering angle, okay. At a suitable scattering angle of phi, okay, you will find that electrons, means the wave nature, okay, there will be a scattering happens, and then whatever the electrons that is, whatever coming out of this one is being collected in a Faraday's chamber, okay. So the Faraday chamber will collect all the intensity of things that is coming out, okay. This intensity will be measured, okay. Whenever there is there will be an intense wave that is falling onto this galvanometer G will show you the deflection in the galvanometer, okay. So this is an experimental setup that was explained by the Davison and GERMER. Okay, so here what we can study is, now come to this one. This is thermionic emission. This is another diagram which is I have drawn. Okay, here you will find in this setup. Okay, this is a up to the emission part, and this experimental setup was slightly modified, and you will find that there is a rheostat here and a potential. See, whenever there is a potential difference that is given to the electron, then the electrons will be attracted towards this side and they can fall easily on the target material. So without a potential difference, the flow of electron is very, very slow. Okay, so more potential difference were given on this side using a rheostat setup, and this rheostat can be adjusted suitably, and therefore a potential difference of 54 volt were tried. Different voltages were tried from 40, okay, and then 44 volt, 48 volt, 54 volt, and 60 volt. All these different voltages they tried, varying the potential difference. Okay, why potential difference? Because the electrons can be attracted towards the target material and it can hit the target material easily. Okay, so for that purpose, the potential differences were applied as 40 volt, 44 volt, okay, and then 48, and then 54 and 60 volt, like this. Okay, so approximately around 54 volt, okay, it was found that the electrons were made to fall on the target material. The 54 volt of potential difference was found to be the ideal, okay, ideal or good potential difference for the electrons to be attracted towards the nickel target. And also they have found at a different angle, okay, incident angle of theta. Okay, they tried to vary the target material, moving the target material in a rotating table, and they found that at different angles they tried, and they found that at an angle of around 50 degree, okay, this one collected here, the collector could collect more number of electrons on this particular thing. Okay, so the angle 50 degree was considered to be a correct one or an ideal one. Okay, so now this, what does the experiment shows? Okay, the X-ray analysis, here the X-ray analysis shows that nickel crystal, okay, the nickel crystal acts as a plane diffraction grating. This is acting like a plane diffraction grating material, okay, where with the d-spacing, okay, the d-spacing in this was found to be, the d-spacing was found to be 2.15 Armstrong, okay, 2.15 Armstrong, okay. It is like how the X-rays fall on a target, and then the X-ray diffraction pattern is being observed, okay. This is a similar experiment, similar to that of the X-ray diffraction pattern, okay, that they could analyze it, okay. Okay, now, okay, here whatever they got, it is like a current, okay. The current was measured using the galvanometer, okay. This is an ionization chamber, okay, which was moved. This setup was also moved here and there, okay, on an axis, as a circular axis like this. And this ionization chamber was moved, okay, to various position, and the deflection, whatever deflections in the, it is also called as a deflectometer or a Faraday chamber, okay. In different books, different ways there it is explained, but it is actually an electrometer, I can say, which can measure the intensity of the diffracted beam of electrons, okay. So here I can say the intensity, okay, of the diffracted beam, okay. This is after diffraction, okay, diffracted beam of, okay, diffracted beam of electrons, okay, was collected, okay. I'll repeat one more time. By thermionic emissions, electrons were emitted, and a suitable potential difference of 54 was applied by trial and error method, and they found that 54 holes were very correct or good enough for the potential difference to be maintained, so that the electrons will be attracted and made to move towards the target. And when the beam of electrons hit the target material of nickel having a particular d spacing of 2.15 angstrom and at a particular angle of incidence, this is theta is angle of incidence, and with different trials and error they have found at 50 degree, okay, at a glancing angle of 50 incident glancing angle of theta 50 degree, we can get, okay, by moving this Faraday chamber, or I can call it as an electrometer, okay, we can find that there will be an intense diffracted beam that comes out. Okay, the intense diffracted beam is in the form of waves, not particle. That is the conclusion. Okay, here the electrons are moving, that is a particle nature. Electrons are just moving like a particle. But once it hits a target material, you are not getting the electron as such, but you are getting an intense beam of diffracted beam, okay, of electrons only, but it is in the form of a beam of diffracted beam, they say. That means they are now coming out in the form of waves here, okay. That was a proof that Davison and GERMER proved that there is a diffracted beam of electrons with a particular intensity. And as I said, that if this is like the wave incident, this incident wave, okay, when they hit a target material, you will get reflected beam, and some will be transmitted also if they are not hitting it at a particular angle. But those waves which hit the target material, okay, and if they fall on a particular atom plane in a particular atomic site, and if they get hit by those atoms, they get reflected. So these are reflected waves. And if you draw a perpendicular on both the sides, okay, up to this wave is the path difference of this set of waves are equal. And if the path difference is equal, and then we can say that you will get a bright beam of light. Interference takes place, isn't it? Here you will find that interference takes place and you will get a bright beam of light. Okay, so here up to this is an electron falling as a particle, and after here you will get a beam of light. Say that means they are in the wave form. Electrons, you are getting a diffracted beam of electrons only, but that diffracted beam of light produces an interference pattern of it produces an interference pattern like this. Okay, it will be producing an interference pattern like this. Okay, so it is proved that these beams of light are nothing but wave nature of the electron. So this was a proof that Davison and GERMER proved. Okay, so here we could conclude that electrons being a particle, when after hitting the target material at a glancing angle, they are moving in the form of wave. Okay, this is a proof. Okay, now the wave nature is being explained here, but what about the particle nature? So to prove that the electrons are in the having the particle nature, we have to also substitute. So first let's finalize this with the wave nature. Okay, they found the wavelength of the wave that is being emitted. Here I said intensity of the diffracted beam of electron. Okay, so let's find out the wavelength, because we say that the matter wave has a wavelength lambda, isn't it? So what is the wavelength lambda according to de Broglie's concept? It is lambda is equal to h by p. That is for the particle nature. Okay. Now for the diffracted beam of electrons over here, according to the X-ray diffraction pattern, what is the formula? So let's see this formula. Shall I rub this one now? Okay. So let us complete this part of the wave nature. Okay, by taking this formula of, what is the formula of the X-ray diffraction? Okay, n lambda. This is for the wave nature. I'm writing for the wave nature of the diffracted beam. Okay, of the diffracted beam of electrons. Okay, that is the electrons that are getting diffracted from here. Okay, now what is the formula for the X-ray diffraction pattern? This one. So n lambda, by Bragg's formula, we know that n lambda is equal to 2d sine theta. Okay. Now what is theta? Theta is a glancing angle. Okay. How will you get the glancing angle? So it is said that, see here in this figure, you can find it out. The incident angle was 50 degree. Okay. So the incident angle here is 50 degree. Okay. So on both the sides, it will become 65 degree each. So that it will become, the entire one will become 180. Okay. Then theta will become 65. Okay. I'll repeat. So this angle was 50 degree. Okay. As predicted by this experiment. So the incident angle on this side will be 65 degree and the diffracted angle will be at 65 degrees. So that together it will become 180 degrees. So theta will become not 50, but it will be 65 degree. Okay. So I will write here. Okay. As, and what is the D value? I have mentioned here. It is around 2.15 for nickel crystal. Maybe for another one, whatever material that has been taken in this experiment, it is given as 2 into, okay, here it is D value is given as 0.91. Okay. And then into angle sine 65 degree is going to be equal to, maybe in this experiment it's not nickel, it may be a copper crystal, so that value is given here. Okay. So here, this is a little modified experiment compared to this setup. Okay. So this crystal value, they have taken it as 0.91. Okay. Now, if you multiply the sine 65 degree will be equivalent to 0.903. Okay. 0.903 Armstrong. Okay. So multiply all these things values, you will get it as lambda value equivalent to, okay, after multiplication, this value you will get it as n is equal to 1. When we put it, you will get lambda value is found to be equivalent to 1.65 Armstrong. Okay. That means the diffracted beam of angle that is coming out. Okay. Now here the electrons are coming in the form of wave. Okay, as a intense diffracted beam like this. Okay, continuous beams of light, beams of electrons are coming and they are having a wavelength of 1.65. Okay, so that was the experimental proof that David and GERMER did. Okay, and also they also have to simultaneously prove that the particle, this is the wave nature. They said that the electron beams are coming out with the wavelength as a wave with the wavelength of 1.65 Armstrong. Now, we also have to prove that the electrons are moving in the particle. Up to this, before hitting the target, they are moving like a particle. Okay. So particles wavelength also we have to calculate, because as per de Broglie concept, he said that the particles are embedded in the wave. Okay. So we need to prove that particles are also having, are moving in the form of wave. So according to the de Broglie concept, what is lambda? The matter wave, the wave nature. This is particle nature I'm going to talk about here. Okay. Then I will conclude that both are, the values of both found out from the values are equal. Okay. Now particle nature of electron. Okay. So if the electrons are moving like a particle, but also having a wave pattern. Okay. That means they are also having a mass. Okay. And they also have a momentum because they are moving. They have a velocity and they are moving with a particular speed. Okay. So we need to use this formula according to de Broglie. What is the wavelength of a matter wave? Lambda is equal to nothing but h by p, Planck's constant divided by p. P is the momentum of the moving electron. Okay, momentum of the moving electron. Now I will rub this. Okay, the momentum of the moving electron. Momentum of the moving electron. So in that case, okay, the momentum is equal to m into v. Okay, And so we need to use this formula. Lambda is equal to, okay, and P, what is the value of P? H divided by this P, the formula is given by 2 into M into E. Okay, so now put it into the format. Now what is the value of H? H Planck's constant value is given by lambda is equal to 6.6 into, okay, approximately into 10 to the power of minus 34. And under root of 2 into, what is the mass of the electron? It is 9.1 into 10 to the power of minus 31. What is the energy? E is equal to, okay, that value, we will give it as in electron volt, no? E into V. The moving electron has a value of EV, okay, but the potential difference, it is being taken to the other side. So E into V, if you calculate and substitute here, it will become 1.6 into, okay, 10 to the power of minus 19, 9.1 into 10 to the power of 13 into 1. Okay. Now, if you do this calculation, again, you will get the value of lambda is equal to, okay, if you multiply and divide it by this value, you will get this value as 1.66 Armstrong. Okay, so here you are able to see that the lambda value of 1.66 is approximately or almost equal to the value of lambda is equal to 1.65, which value was got by the X-ray diffraction pattern. Okay, as an intense beam with a wavelength of 1.65 Armstrong by GERMER and Davison. Okay, so the particle nature of the wave also has a wavelength of 1.66 Armstrong, as well as the wave nature of the electron, diffracted beam of electron after this diffraction in the experiment also has a value of 1.65 Armstrong. So this, both the values are equal to one another. So this proves, okay, these two proves that the electrons before hitting the target is moving with the wavelength as a particle with a particular mass and with a particular momentum, okay, and have the value of 1.66. So it proves the particle nature of the electron, and this value proves the wave nature of the electron producing the intense bright interference pattern. Okay, so Davison and GERMER, they showed it with a diagram also. Okay, so this is a proof that the electrons behaves as a particle with a wavelength of this value, as well as they also behave like a wave with a wavelength of 1.65 Armstrong. Okay, so this experiment clearly proves the particle as well as the wave nature of the electron. Okay, and to conclude this part of this one, they also graphically put this one, Davison and GERMER. Okay, they draw this direction of the incident beam. Okay, initially they got like this with difference, with the different potential differences, no? And with the direction of the incident beam. Initially, the pattern was not like a wave, but it was like this. Okay, the diffracted beam was having a wave pattern like this. Okay, but with varying the voltage, okay, of 44 volt, they could get a pattern like this. Okay, and again varying this voltage to 48 volt. Okay, initially I said no, here in this diagram the potential differences were varied in order to have a proper wave pattern. Okay, at 48 volt again it was like this only. Okay, so at around 54 volts, at around 54 volt exactly, they could get a wave pattern like this. Okay, do you see this? This is a diffracted image. Okay, the image, if you see it in a this way, see in an X-ray, when you see X-ray diffraction pattern, you will get a pattern like this. There will be a maxima here, okay, where the intensity is high, and there will be two minima. So this figure also is like this. These are two minimas. Okay, these are minimas, I can say minima, or darkness, I can say. And this top portion, like a wave pattern, is going to be the maxima, where the interference pattern is giving rise to a bright spot, giving rise to a peak value. Okay, so if I have drawn this diagram in this way, okay, changing it in this pattern, so you are able to see that this pattern is nothing but a diffracted pattern, diffracted X-ray pattern. Okay, diffracted XRD, they say, X-ray diffraction pattern. So okay, so ultimately I can say that at around 54 volts, you are able to see a pattern of wave nature, which is equivalent to a diffraction X-ray pattern. Okay, so this proves that at 54 volt and at an angle of 50 degree, okay, you will be able to get in the nickel crystal a proper X-ray diffraction of beam of light with a wave pattern like this. And so this proves that there is a wave pattern for the electron after diffraction from the nickel crystal. Okay, and when they tried with a higher volt, 60 volt, okay, this pattern was not coming like this, but it is changing. Okay, it was almost changing like this. So they found out that 54 volt was an ideal potential difference. Do you remember in the figure, the rheostat was adjusted suitably and the potential difference of 54 was maintained in order to get a proper wave pattern. Okay, so I would like to conclude this class by saying that Davison and GERMER experiment was an important experiment. It was very important to prove that they proved that the electrons are also moving like a particle with the particular momentum, okay, and with the particular mass and with the particular velocity. And they proved the lambda value was 1.66. And also they tried and proved when it was allowed to hit a nickel or a copper crystal with a particular d-spacing value, they were able to get a wave pattern like this, which is similar to an X-ray diffraction beam at the proper potential difference value of 54 V and with an angle of theta 50 degree. Okay, so this they have proved again, and they substituted the value of the d spacing and the theta of the particular crystal that was chosen, and they also found the lambda value was 1.66 angstrom. So they proved both the values of the particle nature of the electron as well as the wave pattern of the electron. So this was a very, very important experiment that proved the particle and the wave nature of electron. Okay, so I will conclude this class. Hope you have understood it. Thank you for your listening.